Okay, we will now start the energy bands in solid. And at the beginning, we would look at a qualitative approach, just qualitative, without going into calculations or using equations. So, when atoms are brought together and bond to form a solid, so now we're talking about forming a solid from a group of atoms. Normally, we expect an atomic number density, the number of atoms per cubic centimeter, is of the order of 10 to 22, 10 to 23 per cubic centimeter. So you bring an enormous amount of atoms, you bring them together, 10 to 22, 10 to 23 atoms together to form a solid. We discussed in the previous chapter the energy states of electrons in an atom. We said in an atom we have different shells, and always in the ground state, electrons will be in the ground state energy levels of the atoms. So, if we have 10 to 23 atoms per cubic centimeter, and we have electrons staying in the ground state energy levels, then per cubic centimeter, we have 10 to 22 to 10 to 23 identical levels for these atoms that form the solid. When they are isolated, these energy levels are again isolated uh, in each atom individually. But when you bring 10 to 22, 10 to 23 atoms together, now you have 10 to 22 or 10 to 23 per cubic centimeter energy levels in a band when they are in a solid. So this is here what we show is what the 1s energy level in a single atom. Okay, now if we bring 10 to 22 atoms per cubic centimeter, then we have 10 to 22 1s states per cubic centimeter. So we have all these electrons per cubic centimeter in all these energy states. Electrons have a very strange property. They don't like to stay in the same state with all parameters equal. In other words, they don't like all to have the same equal energy, equal spin, equal momentum, etc. They like to occupy different energy states or different uh, states that are defined by different parameters. So, when we bring those 10 to 22 atoms together, what happens is that these energies of the different 1s, 10 to 22 1s, start vary a little bit. So they start to change a little bit so that they can be different energies so that each electron can stay in a different energy. So if we have one energy for one atom, when we bring together 10 to 22 atoms per cubic centimeter, these states now is spread out, okay, in energy so that they become different from one another. And they spread out in a very, very thin energy range, in a very, very narrow energy range. Okay? So, in that thin energy range, maybe only one electron volts, that's the spread in the energy states, that makes, a band of width, maybe around 1 electron volt. And within this band, we have different energy states that are different from one another, and their number is about 10 to 22 or 10 to 23. So these energy states are really, really very, very minor change, very, very small change from one another. So they appear like continuous energy states. So here is what I mean. This is an energy state in an atom. When you bring 10 to 22 atoms together, then they spread out. So you have all the states in this range, okay? And then this is the second level in a single atom. When you have 10 to 22 atoms together, then this single level is spread out. And then you have another level, atomic level, then it spreads out. And then a third level, it spreads out. So what is happening is you have a spread out of energy states in this region, and then you have a spread out of energy states in this region. So this is called energy band, and this is called energy band. So it's like continuous energy states. And this happens because you're bringing 10 to 22 atoms together per cubic centimeter. So you get bands instead of single levels. Look, what we have in this picture here are the states of a single atom. Okay, these are states of a single atom, n equals 1, n equals 2, n equals 3, n equals 4, etc. Now, which is what we have here, okay, when you bring them together, the n equals 1 states spread out to 10 to 22 states in a band. And then all of these upper states also spread out, and the bands overlap with one another. So that's a qualitative approach. What we discussed here is a qualitative approach. We just said because the electrons do not like to have the same energy, what happens is that they prefer to spread out in an energy. When you bring them all together, when you bring all these atoms together, they spread out and they form what we call energy bands. That's a qualitative approach. Let's look at the formal approach. When we say formal approach, we mean we need to do a little bit of analysis, mathematical analysis, and we need to do a little bit of equations and solutions of Schrodinger equations. So what we're going to talk about here is applying quantum mechanics to the problem of a solid. So we have to make some assumptions. And again, you are not asked to know exactly how to solve this quantum mechanical problem and how to obtain the energy bands. But I just want to give you outlines for the model that we use and the model for the solution so that you can understand, how people arrive at these energy bands in a formal way, in a formal approach. So electrons' motion in a crystal will now be considered using quantum mechanics. So the formal approach is to use quantum mechanics. Okay? And using quantum mechanics means using Schrodinger's equation. Now, we are going to focus on a single crystal. We discussed in the previous class what we mean by single crystal. Single crystal is a periodic crystal where you have regular, uniform periodicity throughout the crystal. So what you have is you have periodicity throughout the crystal. So we are going to view the crystal as a periodic arrangement of positively charged ion cores. So what we're going to do is each atom, these 10 to 23 atoms per cubic centimeter, they will be arranged periodically. And the core of the atom, which is all the nucleus of the atom, as well as all the electrons around, except the electrons in the outermost shell. That is, the electrons that can be ionized, they leave the atom, and then they leave behind an ion, which is positive ion core. Okay, so these are the ion cores, and these are sitting periodically to form the crystal, and these are sitting in the lattice points. Remember the lattice points we talked about? And then we look at the potential energy, okay, of, of a valence electron in an isolated atom, okay? And then from there, we try to develop a model. So let's look at the diagram. This is a single atom here in A. So it's a single atom. Let's assume that this is the core. And what do we mean by the core? We mean all the nucleus with the protons together with all the electrons in the inner shells of the atom. And then we assume that the electrons in the outer shell, or just to be more simple, let's assume that there is only one electron in the outermost shell, and this electron becomes free. Okay, so the potential by this electron is going to be the Coulombic potential, which is the 1 over r potential, which looks like this dotted line. That's for a single atom. Now, let us have a periodic array of these cores, and we're only going to consider one dimension. So it's only the x-axis. Okay, so I'm going to assume that my crystal only extends in the x-axis. Okay, so I'm going to ignore any three-dimensional aspects of this problem and just focus on my x-axis, which is in this direction. And then you can see clearly that the cores are periodic, right? That's the property of single crystals. They repeat themselves equally. And all these cores are positive charged, okay? And each core contributed a free electron. So the electrons are in the outermost shells are free, okay? So these are free electrons donated. And if they are positive charged cores, this is the potential 1 over r at each core. So what I'm doing is just repeating this potential up here. I'm repeating it here for each core. So this is what the potential looks like, okay, around each core. Okay, now this is a very difficult 1 over r is a very difficult dependence, and it's a very difficult potential to put in Schrodinger equation and try to solve. So the easiest way to do this is to actually make it simpler, approximate it. So how do we approximate it? You know, these are potential wells, but they go as 1 over r. So how about making them rectangular? That's a very nice approximation. Now, this is the depth of each well. So this is the depth of each well. It's just like the quantum wells we talked about, okay? The quantum well structures of confinements we talked about in chapter 1. So this is the depth. Let's assume, let's make this pure rectangular, and let's make the depth constant equals u naught. Okay, and then repeat this periodically at each atomic core. So this is the potential. So this is my u, and my u has two values, a value here and a value here, and another value here which repeats itself the same at this value, and a value here which is the same at this value, and a value here again, and a value here which is the same at this value, right? So it's periodic. And how do I look at the periodicity? I can look at the width here as B and the width here as A. So this is again B, this is again A, etc. So I can write this potential in regions, right? So in region 1, okay, in region 1, I can call this, uh, uh, let me see here, which one I call, in region 1, okay, the potential is 0. No, okay, so this is region 2, actually. This is region 2, and this is region 1 here. Okay, so if you go back, in region 1, the potential U is 0, which is for 0 less than x less than a. Let's go back and look that, which is this position here. So this is x equals 0. Let's say we start from this point, and this is x equals a. So in the region 1, from x between 0, x and a, it's u equals 0, and it repeats itself with this periodicity. So this is the periodicity. In region 2, which is this, or even this is region 2 here also, okay? Now the potential is u naught, okay? So if you go to region 2, it's u naught for minus b x 0, etc., and it repeats itself. And this is Schrödinger equation for the time-dependent part, psi, okay? And so for our potential, we have to put in this. So this is a periodic potential, and this model is called Kroneck-Penny model, right? So this is a very simple model by those two Dutch scientists who are Kroneck and Penny. They developed this model, which is an easy model. Okay, so we now solve the Schrödinger equation. Now, I'm not at all saying that this is a simple problem to solve. This is quite an involved problem, and it actually calls for many definitions of polynomials, etc. The good thing is you are not responsible for knowing the solution of this problem, even though it is very well laid out in these notes. So you could easily follow them in these notes, and you could easily figure out, how to solve this problem. So this is the time independent Schrödinger equation. This is how we get it psi. And this is the Kroneck model, Kroneck-Penny potential model, which is a very easy model. It turned out, with a little bit of mathematical struggle, people can solve this. Okay. Also, I want to remind you from Schrödinger equation or from quantum mechanics, the time-dependent part is always of this form, e to power minus I, e over h bar t. And E is the total energy, and E can be written as h bar omega, where omega is the frequency of the wave function. Okay. Now, going back to this equation here, to solve it, we have to try this type of solution. And this type of solution are called block functions. And the only trick here is it's an exponential function multiplied by a periodic function. And this periodic function, u of x, is called the block function. Again, it's a special function which has the same periodicity as that of the crystal. Now again, it looks or it sounds all very easy when I say it, but it took people quite a bit of time, to figure out all these solutions and to work out these solutions. So I'm not at all suggesting that these are all trivial. Okay, so the solution is quite involved. And you can go through the solution in the following slides. And you can impose well behavior. of the wave function because it has to be well behaved to have any physical meaning. In other words, it has to be continuous. Its derivative has to be continuous, just like what we did, when we looked at the previous solutions, like the potential barrier problem. As I said, I'm not going to dwell on the solution and the details of the solution simply because this is not a physics class. I'm just outlining the approach people use to get to these solutions. So, again, what happened is when you go through the solution, and again, this is a slide that tells me the solution, is you quickly arrive at a situation which we discussed qualitatively in previous slides. And the solution that you get when you apply all the math correctly, if you plot the energy versus k, the wave number, for the energy of the electron, what you find is that the energy of the electron is continuous in the range k equals minus pi over a to k equals plus pi over a. The electron can take any energy practically in this range. And the energy is parabolic, as we can see it here. Okay? So this is allowed energy states. Any energy here can be taken by the electron. Then immediately in the region minus pi over a and the region plus pi over a at these two particular wave numbers k, there is energy gap. Okay, there is a gap in energy, which is this gap here. Okay, this gap in energy can never be occupied by an electron. So this is called forbidden energy gap. And then again, followed by this range of energy, which is continuous from minus 2 pi over a to minus pi over a, and from pi over a to 2 pi over a. This is again a continuous range of energy that the electron can take, followed by a forbidden energy range that an electron can never take, then followed again by a continuous energy range. So this comes from the solution of Schrodinger equation. Okay, when we apply, the Planck function, the periodicity, etc. And I want to remind you something that is very important. We have 10 to 22 atoms per cubic centimeter. And let's assume that each atom contributed one electron and kept all the other electrons. So it's still the core of the atom, the ion is going to be positive, and we have one free electron moving in this periodic potential. So we will have something like 10 to 22 electrons moving in the periodic potential. Now, so the electrons will have the periodic potential, will see the periodic potential, but there is something else very important. If you have 10 to 22 free electrons moving, it's not only attraction to the positive core. These electrons repel one another because they are negative charge. So the Coulombic repulsion force between these electrons. You can see that we're ignoring this force. We ignore 10 to 22 Coulombic repulsion forces. Now, this is unrealistic. This is not the right thing to do. So this model is very simplistic. This model assumes only one electron. Forget about the remaining 10 to 22 electrons. It's a model for one electron in this periodic potential. So it's not the exact solid. For the exact solid, you have to add the Coulombic force from the repulsion of electrons with one another. We are ignoring that. So we are getting a very, very a very idealized case. A solid with all these periodic positive course with only one electron, one free electron. So only one free electron moving in this. So that's why it's called the one electron model. But it's still, the solution that we get describes what happens in a solid, in a crystalline solid very well. So the bottom line is you have energy, continuous energy bands or states, followed by forbidden energy gaps, followed by continuous energy bands, followed by a forbidden energy gap, etc. So what we're saying here is that there are energy values for the electrons that they can never have, which are these energy values in a solid. So these energy values are called energy gaps. This is not very different from an atom. If you have a single atom, what we found is you get N1, N2, N3, right? So one first shell, second shell, third shell, and each shell has an energy, E3, okay, E2, and so on, right? E3, E1, and E2. So just like in an atom, okay, you have allowed energy states for the electron, and then you also have forbidden energy states. Electron can never take any energy in this, and that is what we call quantization. Quantum mechanics come from the fact that you have quantization. So it's the same thing happening in solid. You have quantization, you have energy gaps, forbidden energies, but then instead of having one single state and one single state here, you have continuous states, right? So the electron can be in any one of these energies, okay? So that's why we call them, instead of just saying one energy state, we say energy band, because we have so many energy states, okay? So that is the picture. Exactly what I've been telling you is written in this slide. So if you go through this slide, it exactly has what I told you in the previous slide. So this is the picture. Forget about the k-axis, the horizontal axis. Just look at